Hi there, and welcome to another chemistry lecture. Today we're going to be learning about bonding, and it's a pretty interesting subject that has some varying degrees of complexity to it. So we're going to talk about the basics of what makes a molecular bond versus what makes an ionic bond. And we're going to talk about that gray area in between because there's really more of a gradient than you probably learned when you were in physical science. And we want to make sure you understand the subtleties of bonding today a little bit more. Okay, so today I think you're going to enjoy this. This is our intro to chemical bonding. And our objectives today, we want to look at ionic bonds, right? And we probably learned this in physical science, but we want to talk about those as electron transfers or attraction between positive and negative ions. And then we're going to talk about covalent bonds. And we're going to talk about that word sharing and how they're sharing electrons in the valence shell to get an octet. You remember that a little bit maybe. And then we're going to classify different compounds as ionic or covalent based upon various formulas. And we're going to look at the fact that it might be a metal-non-metal combination for ionic compounds and two non-metal combinations for covalent compounds. And then we're going to look at the different types of bonds based upon their electronegativity differences. And that's where we're getting into the nitty-gritty of the gray stuff, where we have a line that might not be so gray. And then we want to talk about the difference between a polar and a non-polar covalent bonds. We've got lots of different types of bonding that we want to talk about here today. Okay. So you will be successful if you can describe ionic and covalent bonds in terms of electrons. If I give you a chemical formula, you can identify whether it's an ionic or covalent compound based upon the types of elements that are present. And if I give you a chemical formula, you can determine the electronegativity difference between the elements using the periodic table. Okay, and then state whether or not it's going to end up being an ionic bond, a polar covalent bond, or a non-polar covalent bond. And then you'll be able to describe the difference between polar and non-polar covalent bonds. All right, so the big idea here is atoms are going to connect. They don't exist by themselves in nature. They're going to want to connect with each other. And we have this connection that happens, and we have to ask ourselves why. Why is this happening? Well, it's to get to a more stable energy state, right? Chemical bonding is going to be this attraction between the nucleus of one atom and the valence electrons of another atom, right? That's what chemical bonding is, one way or the other, whether it's covalent or whether it is ionic, okay? We also can talk about chemical bonding being that force that holds the atoms together and makes them more stable, okay? It gets them to a lowest energy state, a lower potential energy state. That's one of the things you want to remember when you're thinking about the actual reason that atoms are bonding together is because they want to lower their potential energy state, and it's more favorable for them, more stable for them. All right, what do we call bonded atoms? We call them compounds. Okay, now we can have ionic compounds or molecular compounds. Sometimes we'll use the word molecular, sometimes we'll use the word covalent. Molecular and covalent are interchangeable with each other here, okay? So let's talk about ionic. Bonding that results from the electrical attraction between cations and anions, and covalent, the bonding that results from the sharing of electron pairs between two atoms. What's the picture going to look like for these? On the ionic side, if sodium is given one of its electrons to chlorine, now sodium is positive, chlorine is negative, like two parts of a magnet, north and south, they're attracted to each other, they're going to come next to each other, okay? And so these guys are going to hang out because of opposite charges. That's ionic bonding. What about covalent bonding? Well, we still have the positive nucleuses and we still have the electrons, but in this case, they share electrons so that they can occupy a full orbital, okay? So you remember how the electrons go up and down, right, on the orbital diagrams? Well, in this case, this is going to fill up that valence shell, and when they fill up the valence shell, they'll do that as they both share. And so we consider that a covalent bond if they're sharing the electrons between them fairly mutually, okay? Not always completely mutually, but fairly mutually. All right, so what is going to influence bond polarity? We learned about electronegativity last chapter, and it's important that we still remember what that is, because that is going to be one of the biggest factors that we deal with here, okay? Electronegativity, remember, is that attraction that atoms have for shared pairs of electrons. The higher electronegativity atom, okay, it's going to have this little symbol here. It's kind of hard for you to see that. So let me put that up on the board so you can see that a little easier. Okay, it's kind of looks like that. Okay, and then this one that has a slightly positive charge or has a lower electronegativity is going to get that symbol. Okay, and so that's the symbol we use in chemistry to signify the atom, the part of the atom that has a charge. Okay, so the higher electronegativity atom is going to get this. The lower electronegativity atom is going to get that. It's not quite the same thing as positive and negative, but it's basically the same thing. Okay, it's just not as extreme. It's just showing us that yes, we do have some positive side and some negative side, but they're still sharing. So if it's ionic, we use a plus and a minus, okay, and we just don't have that little other symbol. But if we have a covalent compound, we use this symbol with the plus and the minus, okay? All right, so, and that's a Greek letter, by the way, so that's where that symbol comes from. All right, so ionic versus covalent bonding. The difference, okay, if we wanted to do a quick and dirty way to say, hey, what is an ionic compound, we would say, well, look, if it's a metal and a non-metal together, it's ionic. And if it's a non-metal with another non-metal, then it's covalent. That's the quick and dirty way, and it works a lot of the time, but it doesn't work all the time, okay? So we're going to show you today another way that is more accurate, but quick and dirty, metal non-metal is ionic compound, and then two non-metals is a covalent compound, okay? So that continuum, if we're not going quick and dirty, okay, then we want to talk about going from an ionic compound to a polar covalent compound to a non-polar covalent compound. So this is like more ionic in character, and this is the least ionic in character. This is the more transfer, and this is the least transfer, okay? These guys are sharing really mutually. These guys are not sharing mutually, but they're still sharing, and these guys are not sharing anymore. That's the idea here. The ionic is a transfer. These two are both sharing, but they're sharing in different ways. So if I look at this little table over here, okay, or this little graphic, you can see I have this numbers here, 0, 0.3, 1.7, and 3.3. Now, if I have an electronegativity difference between two atoms that is anywhere between 0 and 0.3, including 0.3, then I'm going to call that nonpolar covalent. If I have anything between 0.3 and 1.7, I'm going to call that polar covalent. They're sharing, but they're not sharing as equally. I'm going to show you some graphics here that'll let you see that a little bit. And then if I have something from 1.7 to 3.3, I'm going to say, yeah, they're not really sharing anymore. One of them has pretty much pulled that electron all the way over to itself. And so we're going to be calling that an ionic compound. Now, again, this is a continuum, right? So we did arbitrarily choose 1.7. Okay, and it's not completely arbitrary. There was a reason for it. But we pretty much are saying that once you hit 1.7, we're going to call it ionic. Even though, you know, if something were 1.6 and something were 1.8, they're very similar in terms of how they're dealing with the electrons. We are choosing 1.7 as the point at which we're now going to call it ionic. So you can see that by man's definition, we're suddenly calling something ionic instead of covalent. What's the real difference? They're still bonding. They're still interacting with their electrons. It's just that one of them has pulled the electron close enough to itself at this point that we're going to go ahead and arbitrarily decide that's close enough to call it ionic. We're going to call it, it's pretty much taken that electron away from the other one, but they're still next to each other. And the interesting thing is those ionic compounds are actually strong compounds. They have really strong bonds to them. We'll talk about that here in a little bit. All right, so again, the electronegativity difference, if you are between, EN stands for electronegativity. If you are greater than 1.7, ionic. If you are between 0.3 and 1.7, you're polar covalent. And we're just using 0.4 in this case, because 0.3 is still considered nonpolar covalent. If you're between 0 and 0.3, it's nonpolar covalent, okay? But if you were something like, you know, 0.31 or whatever, then you would still be considered the polar covalent. But we don't really have those numbers because our electronegativity values just have one decimal, so that doesn't really even happen. All right, so here are 3 examples of these different types of situations where we have these bonds, okay? The first one over here, they're equally sharing. And notice the electron cloud, okay? That's what they're trying to show you by the shape of the atom. The electron cloud is equal between these two. They're sharing those equally. They both have similar protons in the middle pulling on those electrons, so they pull on them equally. But here, we have something quite different. The B atom has a stronger nucleus with more positive charge, a more effective nuclear charge, and then it's going to pull the electrons away from A, and basically, although they're still sharing, the electrons are mostly hanging out around B. Now they're hanging out a little closer to B, right? And now, if we look at ionic, it's actually taking the electron, and now is what we're saying, it's taking the electron, but these guys are still close to each other. Now, they're showing it like all of a sudden these are further apart. That's not necessarily the case, okay? But what they're saying is that the electron is now over here all around B, and it's not really interacting with A much at all, okay? So the bigger, pull that this has, the more it's going to pull the electron toward itself. So this would be like fluorine, with sodium or something like that, okay? Now, what does that look like in terms of compounds? I'm going to show you that broken down even more here in a second. But if we're drawing a model, what is this, like? If this is a model, for instance, of sodium chloride, okay? This is a typical cubic crystal that is going to be ionic in nature. And the bonds themselves, these little bonds right here, the little green part here between the two atoms, that's the bond, okay? And you'll notice that here is a molecular compound. This is graphite, and we're still using the same green thing to represent that bond. And you notice that the distances are the same for those green things. So is there really, much of a difference in terms of the model? No. When we do these models, especially, when we're actually building stuff like that, we're still showing the basic attraction being the same. Now, the bond lengths are not always going to be the same between different types of atoms, but we still usually typically show them about the same with those models. So let's look at bond polarity. I really like this little animation that we have, these two dogs. These two dogs are coming in, and they're both the same, and they both have a bone. And so those bones are representing the electrons. The dogs are representing the atoms. And as they come together, they say, hey, and they realize that they both want to have part of that bone, right? It's not enough for a dog to have one bone. It needs as many bones as it can have. And so in this case, they say, hey, I can share mine. He's like, yeah, I can share mine. And they share them equally. Now, this is a good example of chlorine, where the effective nuclear charge of both of these is +7 with an equal electronegativity. And so these guys are sharing equally between each other. And so that's why they both have their mouths on about an equal amount of the bone, okay? So electrons are shared equally, symmetrical electron density, and they usually have identical atoms for this to happen. In order for a non-polar covalent bond to happen, it's probably going to be identical atoms, just like these are identical dogs, okay? Now, this is the electron cloud once again, okay? Again, even sharing. Let's look at our next one. This is our polar covalent bond. Notice that we don't have the same dog anymore, okay? And that's typically what's going to cause an unequal sharing. One of the atoms, in this case fluorine, is going to have a much stronger pull on those electrons because it has a much bigger effective nuclear charge. Now look at that. He's holding, and his mouth is way over the bones, and this dog just barely got a little piece of the bone. He's like, okay, you can have my bone, but I get a little bit. Right? I mean, he's just hanging on just by a little. Now this is hydrogen fluoride, and this is a good example of polar covalent bonding. One atom that has a high electronegativity, one atom that does not as high of electronegativity. That difference is somewhere between 1.7 and 0.3, and we'll talk about what those differences are. But that's a good animation to describe polar covalent bonding. Again, here, we use that symbol, right, to show that we've got a partial charge, and notice that the electron cloud is more over this atom, that would be your fluorine, than over the hydrogen, okay? And so this is effectively a negative charge part of our atom, and this is effectively a positive charge part of our atom. Not completely ionic, not a plus and a minus, but a partial charge, okay? All right, so now let's look at our ionic bond. In this case, the electrons are not shared. So a big bulldog over here coming in, and he's taking that bone away from the other dog, and he's got both bones now, and that dog's got none. Now, and they're showing the dog kind of, sniveling up to the other dog. Please let me be next to it. Maybe I'll get a bone after he, gets tired of it and he drops it. So these guys are still attracted to each other, right? The dogs are still hanging out next to each other because there is still, remember, this is a positive charge, and these are electrons. And electrons have negative charges, and so they're still going to want to be next to each other because opposites attract. But the bulldog now, this one, chlorine, has taken the electron for itself, okay? And it has basically pulled the electron really close to itself compared to where it was before. Again, notice the distance. It kind of looks a little bit different than what we had before. The distance here versus the distance here. That's not really anything. That's just the graphic, okay? So the distances here are not being demonstrated by these graphics. All right, so we got charged particles, opposite charges attract, no sharing of electrons. This is the transfer of electrons. All right, so let's see if you can figure this out. It says use the electronegativity differences to classify bonding in the following compounds. Now, in order to do this, you're going to need a periodic table that has electronegativities on it. And one of the ones that I've given you in your resources section of the classroom is this periodic table here, and it's got little numbers underneath, okay, and these are on the, if it's underneath the atomic mass, it's got another little number underneath it, and it has these little numbers on it. And so, for instance, if I wanted to figure out the electronegativity differences, then I would have to look up the two different elements that are involved in that compound, and then I would try to do a subtraction problem and figure out what their differences are. Remember that you're doing an absolute value, okay? Basically, you're just looking at the difference between the two types of atoms present. We don't have to worry about how many atoms there are, okay? It's not like you're multiplying electronegativities by the subscript in the formula. That does not happen. You're just looking at the differences of the two atoms. So I look at calcium and chlorine, okay? And so if I look at chlorine, chlorine has a 3.0 electronegativity. Calcium has a 1.0 electronegativity. So its difference is 2. So is that bigger than 1.7? Yes, it is. So what kind of a compound do I have? Well, I have an ionic compound, okay? That's going to be like this one, right? It's calcium chloride. Now, again, if I do it quick and dirty, calcium's on the left side, it's a metal. Chlorine's on the right side, it's a non-metal. Quick and dirty, ionic compound. But we use the electronegativity difference to give us a definitive answer on that based upon definition by man. Chlorine and oxygen. Well, chlorine is a 3.0 and oxygen is a 3.5. That means there's a 0.5 difference, which means that that's bigger than 0.3, but not as big as 1.7. Therefore, this is a polar, excuse me, polar covalent compound. Okay, and so these guys are sharing still. They're not sharing equally. Oxygen is got that 3.5, so it's pulling the electrons a little closer to itself than chlorine pulls it to itself. Okay, so that's how you would do that. And so these are the ways that we would go about and determine whether or not a particular set of atoms are ionic, polar covalent, or non-polar covalent. Okay, so let's see if you can do it. Okay, so it's the time for you to pause it, right, and practice. So pause it and practice and see what you get. All right, and so we're back. Here we've got bromine and iodine, magnesium and iodine. Okay, and we want to talk about what the difference is between what the electrons are doing, and then we're not quite ready to do step number 3 yet. That's going to happen after our next lecture. But let's look at bromine and iodine. Bromine has got a 2.8 electronegativity. Iodine has a 2.5 electronegativity. That's 0.3 difference, right? And so these guys are considered non-polar covalent. They're close enough in their attractiveness for those shared electrons that they're sharing pretty equally. Magnesium and iodine, however, are a totally different story, right? 1.2 for magnesium and 2.5 for iodine. So we're looking at a 1.3 difference. Now that's less than 1.7, and so we can't call this ionic, even though it's a metal, non-metal, situation. All right, and that's something that's important to remember, because this is why we use the electronegativity differences, because it's a metal and a non-metal, and yet according to the guidelines that we have, this is a polar covalent compound, and it's something that you can't just look at metal, non-metal, and it's okay that you think, well, that's a big difference and they're going to be attracted to each other. Yeah, but is it actually an ionic compound? It's actually not. It's actually 1.3 in difference, and so it's a polar covalent compound. Kind of wild, right? So let's look and see if what we have learned is now in our brains. All right. Describe an ionic bond as electron transfer or attraction between a positive and negative ion. Okay, yeah, ionic is electron transfer. Sweet, okay, positive ion, negative ion. We got that, ionic compound. Covalent compounds, sharing. So that they get that full valence shell, they want to try to get to that full octet, right? Yep. Compound can classify it as ionic or covalent based on the formulas, metal, non-metal. Yeah, I could do that. And for the most part, I can get, pretty close to the answers. But like I just saw on this one, magnesium and iodine. If I did that, I'd be wrong if I classified metal, non-metal as an ionic compound. So I always want to make sure I double check that electronegativity. Distinguish between types of bonds based on electronegativity differences. Yeah, now I can do that, and I have a solid, fast rule that lets me know, yes, that's a electronegative difference enough to make it ionic, for instance. And can we distinguish between polar and non-polar covalent bonds? Yeah, it's all about the sharing, right? Polar covalent bonds are not sharing equally, but the non-polar covalent bonds are sharing pretty equally. All right, so now you can check your criteria for success. Can you describe ionic and covalent bonding in terms of electrons? What do we mean by that? In terms of electrons? Oh yeah, it's about transferring versus sharing. Yeah, I can describe ionic and covalent bonds based upon transferring and sharing. Given a chemical formula, I can identify whether it's ionic or covalent based upon the types of elements present. Yeah, we gave you a few of those, right? And for example, MgI2 is going to be polar covalent. Now you can look at a compound, throw a compound out at you, and you can lay, oh yeah, electronegativity difference, done. I know what it is, okay? Given the chemical formula, you can determine electronegativity difference between the elements, state whether the bonds are ionic, polar covalent, non-polar covalent based on that difference. Yeah, we just talked about that, right? Okay, we know those electronegativity differences. I can describe the difference between polar and non-polar covalent bonds. Yeah, equal sharing versus not equal sharing, right? The not equal sharing is going to be the polar covalent. And what does that have to do with anything? Well, polar covalent bonds are going to be things like water. Okay, water is a polar molecule. So when you hear say the things like, hey, this is a polar molecule, it's because of two things. One, it has to do with the actual bonds themselves and whether those are polar. And then also whether or not the other atoms around them are equally pulling in equal directions or not. And so we'll learn a little bit more about that later on as far as polar molecules are concerned. But for right now, you're learning polar bonds. So some bonds are polar, some bonds are not polar, right? And so in this case, we're not showing you, this is graphite, so this is all pure, pure carbon. And so this is all a whole bunch of non-polar covalent bonds. Okay, but if we were to look at something like water, where we have ice here, let me pull this down real quick. So here we have water connected with other water molecules. This is a oxygen molecule. These are the hydrogen atoms, or oxygen atoms, sorry, and hydrogen atoms. And these are the small little covalent bonds that are between them. Okay, now the white ones are what we're going to be learning about with hydrogen bonding. Okay, but here you have the covalent bonds. Now is it polar or non-polar? I need to look and see what the electronegativity of hydrogen is, 2.1, what the electronegativity is of oxygen, 3.5. So that's a 1.4 difference, which means these are polar bonds. Now this is all a part of a polar molecule, but these are the polar bonds that we're dealing with here. Okay, polar bonds as part of a polar molecule. And then you have the attractions that occur there. So that's just a little bit of an example of how this comes into play. I hope that you have learned something today. I hope you enjoyed it, and I hope you have an awesome day. Be kind to one another, and God bless you.